Next we will go over the lateral control or the steering control of the vehicle. Usually there is a reference path that is based on waypoints. Here we have two different ways of achieving those waypoints or generating the reference path. One is straight line segments, so it goes from these black dots are the waypoints set to define the reference path. So you can either draw these straight lines from point to point or then have parameterized curves. The curves are used intuitively more often when you have waypoints that are further apart from each other. It's quite common that the waypoints are very close to one another. You can imagine like 6 points between this turtle bot and the first dot. So then it doesn't really matter to have these parameterized curves. So then it's computationally more efficient to just use straight line segments. And the control, the lateral control goal is to minimize the offset of the current position of the turtle bot in XY coordinates to this reference path. We have two different sorts of errors that we need to minimize. First is the heading error. So it's the difference between the current heading, so where is the turtle headed to, what is the sort of the course, if you think of it as a ship, what's the course of the ship, the turtle bot, and what is the actual course that it should have. So in this example, the turtle bot is looking to the right of this slide, and actually if you look at the reference path here in red, the actual heading or the course should be a little bit to the left. So there is an error between this turtle bot heading here in this cut line between this yellow line. So that is the heading error. Then you have a cross-track error, which is between the turtle bot and the reference path, whatever is the closest distance between those two, or actually, it's perpendicular distance because the heading error takes that into account. That it's not the closest distance. It's the perpendicular distance between the turtle bot heading and then the reference path. So these are the two errors that we try to minimize as we tune or use a lateral controller. There are many lateral controllers, as there would be many longitudinal controllers. In the last section, we just go over some of those. So here we will go over bang bang controller, which is super easy. It's called that because it just has two settings that you can very sharply switch in between. You can use a cross-track PID, so it has a very similar functioning. It functions very similarly to the longitudinal PID control. And then we have some more, how would I say, lateral control specific control algorithms, such as follow the carrot and pure pursuit. Then there's deviation or implementation of pure pursuit that is especially good for if you have a dynamic model of your car, and that's called a Stanley controller, which comes from a Stanford University vehicle called Stanley that was the first to implement this controller. And then in addition, there are dynamic controllers that model predictive controllers that have the entire dynamic model, and based on that model it controls the steering. Actually Stanley is still just a geometric controller, so geometric controllers don't take into account the system physics, only these cross-track error and a heading error, and based on those it tries to steer the vehicle in a way that it gets into the path, and it's not taking into account what's the terrain and what are the vehicle dynamics. So they're much simpler than these model predictive controllers. But in this lecture we won't go over the Stanley or model predictive controllers. So firstly, bang bang controller. In this case we have fixed steering, and it means that if we have this red reference path, if our turtlebot is to the left of the reference path, we will always have the same steering angle. So if the turtlebot is told to steer to the right, it always does the exact same movement until it reaches the reference path. So here the turtlebot would slowly come across the reference path, and once it goes over, then it will do the exact same steering to the other direction. Well, the problem is that when it's really far off, then the steering might be too small, or when the turtlebot is right on top of the reference path, then it ends up steering very aggressively from one side to the other, so there is this oscillating movement when it's near to the reference path. Well, then there is a good question of why we just don't steer proportionally, as you can use the steering wheel proportionally. You don't need to have it like 1 or 0. So you have this range of control in the wheel, or in the steering wheel. So this is just an example of what is the most simplest rule-based controller that you can have to get started if you need to do it fast. And so the cross-track PID controller already utilizes the proportional aspect of a steering wheel. So based on this cross-track error, so the further the turtlebot is from the reference path, the higher the steering command. So if it's really far off, the steering command will be very strong. Well, there are some. This seems pretty good and something that we should just use this. But imagine that the turtlebot is very far off from the reference path. Then let's say that this is the reference path and this is the heading of the turtlebot. So if it's really far, it will get a very strong steering command. And even when it's looking at the reference path, it's heading straight to it, there is still a long cross-track error, so it starts to spin in place. Obviously you can limit that with some rules in your controller, but still if you're heading straight towards the reference path, obviously when you reach the reference path you will go through it, and then you will do this sort of bigger oscillation than the one that we had in bang bang control. And this all stems from the fact that we're trying to reach a point that is right next to us. So the next two controllers, the follow the carrot and the pure pursuit, will handle this with looking ahead, looking forward in the reference path, so that we get rid of all this oscillation. Next up is the following the carrot lateral control. As discussed previously, this is different from the other lateral controllers that we have introduced, with one of the things being that we have this look ahead distance. We're looking ahead in the reference path rather than trying to achieve this point right next to the turtlebot. So the first thing that we do is that we find the nearest spot in the target path, and then we travel along that path the distance of that is predefined before, depending on your use case. What is a good distance. The longer the distance, the more time it takes to come to the reference path. However, then it's the control is much more stable. And then again, if it's a very short distance, then it's aggressive but less stable. It has more potential to oscillate. Okay, so we have this look-ahead distance is a predefined value depending on the use case. And this reference path is constructed of GPS points, for example. And then, as we have this look-ahead distance, then we can draw this line, this look-ahead line from the green line from our turtle bar, our current position to the goal point. And then the thing we're trying to minimize is this angle between the current heading and this look-ahead line heading. And it requires at least a proportional controller. It's not necessarily required to have a full PID controller. Then next up we have pure pursuit, which is very similar to the follow the carrot as of the beginning of it. So the same way as before, we have this look ahead point, a goal point that we're looking to, and in this method we will be using these distances. So the y deviation YL and x deviation XL between the vehicle coordinates and the goal point coordinates. Then we will connect the vehicle position with the goal coordinates with an arc, and the only requirement for that arc is that if you would draw a radius, it needs to land on this y-axis. So if this curve would be bigger, then the radius would be smaller, and if the curvature would be sort of more shallow, then the radius would be much larger. So the only requirement is that the radius is from the goal point to y-axis, and at the same time that means that the length from this spot, from the current turtle bot coordinates to the same spot, is also the radius of this arc. Okay, so having those criteria, we can now determine these three different equations. So what I just said was that this YL and this small distance over here that we're just going to call A, it doesn't matter what would we call it, it has to be the same as this radius over here, because they both are, this is the center of the circle that is here in this crossed or partial lined circle, and that circle has one segment that is this arc. Then we also have two Pythagoras triangles. One is this RAXL over here, and another one consists of this look ahead line XL and YL. So as we turn these around a bit, so the A distance can also be shown in this way, so it's R minus YL. Then we can plug that in to the equation 2 with just putting the A, sort of opening the term A over here. And then if we open the brackets over here, we get this sentence, this equation, I mean. And we can cross out the R2s in both sides. And then we also notice that now we have this Pythagoras triangle of the equation 1, which we can just substitute with L2, and we end up with this expression of minus 2 times the radius times YL plus L to the power of 2 equals 0. And we can put this on the other side and then divide both sides with 2 times YL, so we get this expression. And so now we know the radius of the arc, and gamma is the inverse of that radius, and it's also called a curvature, which is the steering command that we'll give to the turtlebot. There's a lot to take in here. There's a lot of sort of going through these formulas, so you can go through them one by one and maybe do it by hand. I will also do an extra video of me just going step by step, because this is a bit hasty way of showing it, and it took me quite a long time to wrap my head around the whole thing. What is this pure pursuit? So don't feel like intimidated about it, or that you should get it right away. It's something that you need to think about a bit. It's not the easiest, but once you sort of get the hang of it, it's not that difficult in the end. Well, I guess that goes with all of the things that first seem difficult, I guess. In addition to the lateral controllers, I think it's important to know that we also always have this coordinate system that is the turtlebot's own. So if we go back one slide, now we're just looking at only considering the turtlebot's own coordinates. So X is forward and Y is to the left. But in reality, we also need to consider that there are these world coordinates. We can think of them as coordinates. So you have the longitude and latitude coordinates. And so you can think that this is to the right is east, and then up is north. And now that we have this vehicle that is pointing somewhere northeast, before we start to do our calculations, or how do we define the goal point of this reference path over here in the vehicle coordinates, we need to transpose or transform the transform is the correct word, by the way, not transport. So transform the coordinate system of the vehicle into these world coordinates. So luckily there are predefined formulas for this. They are gone through at length or explained at length in different courses, which we won't dive deeper here, but they're called transformation matrices to do specifically this, to transform one coordinate system into another, and we will use this. This is the coordinate system over here. So you take the answer will be what are the coordinates of the goal point in vehicle coordinates, and the delta x and delta y are the differences from the turtlebot current position, and then the goal point, and then just these cosine and sine matrix is just predefined, a standard matrix. You can look more on those if you wish. And after the coordinate transformation, then again the picture looks the same as before, that we have x to the right and y up, or x forward in turtlebot's eyes, and y to the left. And then we can start doing the same, follow the carrot algorithm, PID for cross-track error or poor pursuit, whatever is the algorithm of your choosing. As now we don't need to care about there being multiple different coordinate systems. Okay, to conclude, today we went through longitudinal control, where the point is that we have some sort of reference speed that we want to achieve, and we have the actual speed or place of the vehicle, and we want to make a controller that tries to minimize that error to drive in this way that's predefined. That is our reference. So let's say that this would be like accelerating to 40 kilometers and keeping that speed. So then we try to do this as accurately as possible. Then we had lateral control, where the specific cases for lateral control were follow the carrot algorithm and per pursuit, where the speciality is that we're looking not to the point of reference path that we're next to at the moment, but we're looking ahead to a certain point. And based on that, we can avoid oscillation and make the control more stable in that way.